So good morning to all of you. And today I want to discuss a virtual memory management technique. And in the previous classes, we have seen several memory management strategies like paging, segmentation, swapping. We have seen several strategies. So in all the memory management techniques, what we have seen before, they require the entire process to be loaded into the main memory before you start the execution. Okay, whenever you want to execute your program, you need to store the entire process. The entire logical memory has to be loaded into the physical memory. So either contiguously or non-contiguously. So in some memory management schemes, you want to load them in the contiguous memory locations. And in some, like paging, it allows the program's memory to be non-contiguous. To be non-contiguous. Okay. Now, the virtual memory management technique is a technique which allows the program's memory to be not to be completely stored in the main memory. So you can execute a process which are not completely stored in the main memory. That is the main advantage of virtual memory management technique. Okay. I will share the PPTs. So here, according to the virtual, what is virtual memory management? What is a virtual memory? The entire process that is, you need not store the entire process in the memory. Okay, that is a virtual memory management technique. It allows the execution of a process which is not completely in the main memory. The main advantage of this is the programs that are written by the users, they can be larger than the physical memory. Now the programmer is no longer constrained with the size of the physical memory. So there is more flexibility for the users to develop the programs. That is a main advantage. Okay, so and it also here this separates the user logical memory from the physical memory, because the view of logical memory is different from the physical memory. The entire logical memory will not be placed in the physical memory. So there is a separation of views. And here, memory storage limitations can be freed because the entire process is not stored in the main memory. The memory storage can be, that is, it is limited. You can occupy less memory space when compared. Okay, so this is one more option. There is a more programs can be stored because only 50%, maybe for example, 50% of your program will be loaded in the main memory. So 50%, only 50%. But for example, if you need 10 frames, actually 10 frames your program sizes. So if you are using only 5 frames, the remaining 5 frames can be utilized by some other process. So the degree of multi-programming can be increased. Okay, and also the swap time also, that is the IO time, swap time will get reduced, because instead of swapping the entire 10 pages, you are swapping only the 5 pages. You are loading only the 5 pages. So the load time will get reduced. The memory storage limitations can be freed. And the virtual memory management technique, this is not that easy to implement. If you doesn't implement carefully, the performance may go down. Okay, so it may drop down. The performance may be dropped down. So, in all the memory management techniques, in all the algorithms, what is a necessary condition is, here, if you want to execute your instruction, that instruction has to be placed in the physical memory. This is a basic requirement. Okay, definitely we need an instruction before we start execution. The first approach for this is, for meeting this requirement is, you can place the entire logical address space into the physical address space. So definitely all the instructions will be stored in the physical memory before you start the execution. And other approach is, instead of loading the entire program, okay, entire logical address space, you can approach a dynamic loading. Okay, so you can use a dynamic loading. So it helps us to ease this restriction. So it will help you not to load the entire process into the physical memory. Only the required pages will be loaded into the physical memory. Okay, that is the advantage of virtual memory management technique. Okay, so here having the entire program in the physical memory may not be required always. So, for example, let us take an example. You have at the beginning of the program itself, you have some selection procedure. So, you have different options. So, based on the selection, the particular code will get executed. So, for example, you have some selection options which are never get executed, or almost, or very infrequently they will get executed. So bringing those part of the codes into the main memory, this is useless. This is not advisable. Okay, why to waste the memory? So because they are very infrequent. For example, you might have return code for some errors which very occasionally they will take place. So such code you need not move it because you will not use. And for example, though you acquire also, maybe you don't use the entire memory at the same time simultaneously. Because for example, if you take the compiler, you have a pass one code and pass two code, and you have some common routines. When pass one is required, pass two is not needed. When you are doing with pass two, pass one is not needed. So you can load only the part of the program which is necessary, which is used. Okay, that is called the dynamic loading. Okay, so here, for example, because most of the program, if you observe practically, most of the programs, they may have the code to handle unusual error conditions. Usually that doesn't happen. Unusual error conditions. So why to load all these error codes? Okay, because in practice it is never executed. So why to bring that code into the main memory? Why to waste the main memory? Instead, that space can be utilized by some other processes. And another example is, for example, you will define the arrays. Arrays will be defined of 20 by 20 or 30 by 30. But in practical, you'll be using only of 4 by 4, 5 by 5. Most of the space is unused. Okay, likewise, if you have the symbol tables, you have only very few 100 to 200 symbols, but you'll be specifying the space for 2000 or 3000 symbols. So all these are getting wasted. Okay, so instead of bringing all these into the main memory, you can bring in only the portion of the programs which are needed, which are actually required. Okay, so the ability to execute a program that is only partially in memory would have many benefits. This is called the virtual memory management technique. So because it is allowing the execution of the program which is not completely stored in the main memory. Okay, which is not completely stored in the main memory, you are able to, the technique is allowing to, because paging allows the program's memory to be non-contiguous. Virtual memory technique allows the program to be executed without storing completely in the main memory. Only the wanted portions will be stored in the main memory and you can start execution. Okay, so the benefits of this are, here the programmer is is no longer constrained with the size of the physical memory. Okay, so the users are provided more flexibility to develop the programs for an extremely large virtual address space. Okay, so that's simplifying the programming task, because the programmer is no longer constrained with the size of physical memory. He is given more flexibility to develop the programs, to make the things easier. That is one advantage. And the other advantage is each user program could take less physical memory. Okay, because of this, Because you are not loading the entire program, each user program is taking less physical memory, so that more programs could run at the same time, so that the CPU utilization will be improved, the degree of multi-programming will be improved, okay, and the response time will be improved. Okay, the CPU utilization, throughput, everything will get improved, because you are not loading the entire process into the main memory, only the portions you are moving. So based on that, the degree of multi-programming will be improved. Okay, that's it. And the third advantage is less IO would be needed to load or swap each user program into the memory. Okay, so that it would run faster, because you are not moving the entire logical address space. The less IO will be required, because you are moving partially, you are moving only 40% of your program or 50% of your logical address space. So definitely the IO would become less. Okay, it would be less. Okay, so these are the things. So this is the view, this is the diagram which shows how the virtual memory is larger than the physical memory. See here, by looking at the diagram, you can understand you can view the size of virtual memory and the physical memory. The virtual memory size is very, very large when compared to the physical memory. Okay, and in between you are having a memory map. This is used for the address translation. Okay, so the logical address has to be mapped to the physical address. If that address translation is not done, you cannot access the physical memory, you cannot access the actual data. Okay, so the virtual memory or the logical memory, it is divided to pages, and only few pages will be loaded into the physical memory, not all pages. And these pages, they need not be contiguous, need not be contiguous. And here we have a backing store where the entire program will get resided. Okay, where the pages will get resided. So using this mapping hardware, you can translate the logical address to the physical address. See how big the virtual address space is, how small the physical address space is. So this is how it is. And this virtual memory, this involves the separation of logical memory, which is used by the users, from the physical memory. So it separates the logical memory from the physical memory. Okay, because of this separation only, we can have a large virtual address space which can be provided for the programmers when there is only a small physical memory is available. So the physical memory is different, the logical memory is different, virtual memory is different. Okay, the virtual address space means the logical address space, and this has to be translated to the physical address space, right? So the running a program that is not entirely in memory would benefit both the system as well as the user. And this virtual memory management technique, it can be implemented with demand paging. Okay, it can be implemented with demand paging. So here there are two versions. You have a demand paging and pure demand paging. So demand paging and demand segmentation. Okay, so in the demand paging, what it does is it will not load all the pages into the memory. It will not load all the pages into the memory. It will be loading only the required pages into the memory. So here, as I told you earlier, in the selection program, so for example, you have an option for load the entire program in physical memory. That is one option. What is the second option? Load the pages only as they are needed. That is called the demand paging. See here, how do you execute your program? Provided that those instructions are placed in the physical memory. Okay, before you start the execution. Now, here, one option is you can load the entire program. Okay, so if you load the entire program, what happens? All the instructions will be definitely in the physical memory before you start the execution. And the second approach is You can load the pages as and when needed. Okay, you will not load the entire program into the physical memory. You will be loading only the pages which are needed. This is called the demand paging. So the demand paging system is similar to paging system with swapping, because here we require the, what is the hardware we require? We require the backing store here. Okay, we require the backing store, the page table and the backing store. With the help of this, you can implement the demand paging technique, right? In the demand paging, what we do is, with the initial guess, we'll start with few pages in the physical memory. Okay, so the starting pages will be placed in the physical memory and we start execution. As long as your initial guess is good and as long as you doesn't refer to any pages which are not in the physical memory, everything will go on smoothly. It will be executed as if the entire process is in the memory. It has the impression that the entire process is in the memory, as long as you doesn't refer to the pages which are not in the physical memory. Okay, if you do like that, if it is so, then nothing will, there will be not at all a problem. Okay, so here, bring a page into memory only when it is needed. So then, what are the advantages of this? IO will be less, memory needed will be less, the response time will be fast, and more number of users can share the memory. The multi-programming level can be improved. That's the thing. Now, okay, we are doing with this. If you are these 10 pages, only 4 pages has been loaded into the main memory. Only 4 pages has been loaded, and the 6 pages, they are not here, they are on the backing store. They are in the backing store. Now here, how to distinguish how to identify whether a particular page that you have referred is in the physical memory or not. There should be some way to distinguish which pages are in the physical memory, which pages are not loaded in the physical memory. You should come up with this. All right. So how to distinguish is, here you can use a valid invalid bit. Okay. Each and every page is associated with valid invalid bit. So if that bit is equal to 1, it means that the corresponding page is in the physical memory. If it is equal to 0, it means that the corresponding page is not in the physical memory. So that is the valid invalid bit usage. So here two things can happen. Okay, so for example, this is a occasion where you can transfer a particular program to the backing store, and from the backing store you can load into the main memory. Okay, this is the scenario. Now, for example, if you look at this diagram, at this table, here you have a page table. In the page table, as you have seen already in the paging memory management scheme, the page table will give you the information of the frame where the corresponding page has been stored. It will give you the frame number where that particular page has been stored in the physical memory. That is a page table. So here what we are doing is, each and every page table entry is associated with valid invalid bit. Okay, valid invalid bit. So if that is equal to 1, it means that the corresponding page is in the physical memory. If it is equal to 0, it is not in the physical memory. Okay. Now, for example, now you have referred to a particular page, particular instruction. So thus that instruction refers to a particular page. So now, while you are translating the address, if you identify that the valid invalid bit is 0, what do you mean by this? The corresponding page is not in the physical memory. So how can you access that? It is not possible. Unless you bring in that page into the physical memory, you cannot continue the execution. because without that instruction, without that variable, you cannot execute, you cannot continue with your execution. So this is the problem. So what you can do is, first thing is, you should check whether there is a valid address or not. Okay, so you should check the internal table, okay, which is kept with the process control block, where there is, we need to determine whether that reference is a valid or invalid memory address. Suppose if it is a, if you are trying to access, if you are trying to access a memory which doesn't belong to you, which doesn't belong to you, it's a illegal access. This is not your area. You are trying to accessing the memory location which belongs to the other users. So that is a invalid. So if that is the case, a trap to OS will take place and the process will get aborted. You need to do that. Okay, you cannot continue the process. Okay, you need to abort the process. You need to terminate the process. There is no other option. Okay, but if it is a valid legal address, if it is a valid legal address, then it is a responsibility of the OS to bring in that page, to bring in that page for which you have requested. So unless you bring that page, you cannot continue the execution. Okay, this is the task of the operating system. Okay, so for that, it has to follow some steps. See here, if you look at this diagram, you can have a page table where you have a valid, invalid bits. So for some pages, see here in this particular example, you're having three pages which are stored in the main memory. And the rest of the pages, they are not stored. They are available on the backing store. Only those three pages. What are the pages? Page 0, page 2, page 5. For this, the corresponding bit is valid, and for the rest, they are invalid. Okay. So here, in this, this is the scenario. Now, if you try to access a page which is not in the physical memory. So here, if you try to access a page 1, the contents of page 1 or the contents of page 4, what happens? While translation, it will identify that it is an invalid. So once if it is an invalid, you need to check whether it is a valid address or not. Once you make sure that it is a valid address, what you should do? You need to bring in that page. So for that, what you need to do? You need to identify the free frame. So from the free frame list, you need to identify one free frame, and we need to perform a disk schedule. That is, we need to schedule a disk operation to read the contents of the desired page, and you need to swap into the newly allocated frame. You need to copy the contents of that page into the newly allocated frame. When the disk read is complete, that is when the data has been transferred to the physical memory in the allocated frame, what you need to do is you need to modify the internal table which reflects that the corresponding valid invalid bit is set to valid, because in the page table we need to indicate that that particular page is now in the physical memory. So once this is done, you can continue, that is, you can restart the instruction that was interrupted. So you need to restart the complete instruction. See, restarting in the sense, it is not such simple thing, because for example, you may be, there is a trap to OS takes place either at the beginning of the instruction or at the end of the instruction. For example, you want to perform C is equal to A plus B. You have fetched the instruction, you have decoded the instruction, and you have read the operands A and B, and you have performed the addition also. Now, while storing into this variable C, a page fault occurs. Okay, you have observed that the page is not in, the corresponding page is not in the physical memory. So what you should do? Again, that is, after you bring in that required page, after you resolve this problem, you need to restart the instruction. Restarting in the sense, you need to start right from the beginning. Again, you should fetch the instruction, decode the, see how difficult it is. Sometimes, and hardly it will be less than one instruction, not more than one instruction. It will be less than one instruction. So here, what is a page fault? So and to implement that, what is the hardware support for this demand paging is you require the page table and you require the secondary memory backing store. So the page table should have the ability to mark an entry invalid through a valid invalid bit. So you should have a bit associated with each and every page table entry, and you need to have a secondary storage, that is a backing store. Okay. Now here, what is a page fault? So what do you mean by a page fault? When you try to access a page which is not in the available in the physical memory is called a page fault. So whenever a page fault occurs, you need to bring in that required page and you should start the execution. Okay. So OS looks at another table to decide. Say here, if it is an invalid reference, suppose if the address is illegal, you need to abort it. Otherwise, you need to store it. Okay, you need to get a free empty frame, swap the page into that frame. You need to reset the tables and you need to restart the instruction. This I have already explained. Okay, and these are the steps in handling the page fault. So they are numbered with 1 to 6. The first one. So where that page fault has been occurred when you are executing the instruction load M. So once during the translation, it is accessing a particular page whose valid invalid bit is invalid. So immediately what happens? The second step is a trap to OS take place. Now OS, it checks the internal table, and once it confirms that it is a legal address, third step is it identifies that the page is on the backing store. It reads that page and it brings that page into the free frame. That is a fourth step. Bring in the missing page for which the page fault has been occurred. Next, once you brought that page into the physical memory, you need to update the internal tables. You need to reset the page tables. So making that valid invalid bit as valid or it as 1. So once this step is completed, you can restart the instruction. You can restart the instruction. So these are the 6 steps that you need to follow while when a page fault occurs. So as I told you, the hardware support is the page table and the secondary memory. Okay. So if there is no free frame, so as long as you have the free frames, okay, well and good. You can identify, select a free frame and you can load into that frame and you can continue. Sometimes what happens is if you over allocate the memory, there may be no free frames. So what it should do? It should go for the replacement. So you should replace one of the page with a wanted page, because without that page, you cannot continue the execution. Okay, how to bring in that page? Which page should get replaced? You need to select the victim page. That selection, because one particular page fault, it may refer to multiple pages to be brought in. Multiple page faults may happen. Okay, so whenever a page fault occurs, whenever you want to replace a page, you need to identify the victim page as per the algorithms, as per the page replacement algorithms. Okay, and coming to the performance of the demand paging, here, if P is a probability of page fault ratio, the probability should be very close to 0 if you want to have a better performance. So the P can be between 0 and 1. So if P is very close to 0, then the performance access time, effective access time will be less. So that will be equal to 1 minus P into memory access plus P into page fault overhead plus swap page out, swap page in and restart overhead. You need to take into consideration all these things. For 1 minus P, for which there is no problem, that into memory access. And but for the remaining portions, you need to consider all this overhead. Okay, so this is just an example. Hope everyone understood what is a virtual memory management technique, what are the advantages, and what is a demand paging. Thank you guys.